Morning everyone. So today I'm going to be presenting on some work we've been doing at Swinburne University into developing a low damage partition wall system. So given that we only have 10 minutes today, I'm kind of just going to give more of a broad overview of the journey we went through and won't really get into some of the more detailed findings, but that's all in the various papers that we've written. So just to kick things off, a few acknowledgements. Been working with Java and EMAD from Swinburne, and then we've got a few industry partners, Trucks Metal Framing System, we've been doing a lot of the R&D with, and then we've got also Intex International, who are kind of the commercialisation partner. We had a few research grants along the way as well. So I guess where did the journey begin? So I wanted to kind of start off by putting a few high-rise buildings up on the slide here. You can, for those who can recognise a few of these, we've got the first one on the left, the buildings in Melbourne, back where I live, and then we've got a few in New York and one in London. And so the starting point I want to say is, well, what all these buildings have in common? So we've got, Australia, US, and UK. They're all built using steel-framed partition walls, and they've all had reports in the media of these buildings making noise. So, people are buying $1 million apartments and they're, waking up in the middle of the night to, a noise in the building and they're like, what's going on? So just to kind of give you an idea of what we're talking about here, I'm not sure if the volume will work. It does. So this is we've recreated these noises in the lab, and what you're listening to now is the kind of typical noise that these people are hearing. So, and these type of noises we're talking about, this is 2-3 millimeters of building movement. So people have got these very expensive apartments and they've got quite annoying noise. So what's the source of this noise in high-rise buildings? So non-structural components are, like, without a doubt, the primary cause of this. It's not a structural issue, it's a non-structural issue. And then partition walls in particular are one of the key culprits. So if we look at, a typical building, we have our building cores, and obviously they resist lateral load. And then, we have all these other walls that sit in between. When you're talking about a residential building, you have quite a lot of these walls. And they're kind of built rigidly in inverted commas between the concrete floor slabs. And effectively when the building moves a little bit, these things make noise. So that these walls aren't designed to take the lateral load, but they obviously go for the ride with the building. So when we look at conventional construction, what does it look like? I'm sure most people have seen this. We have our steel frame walls, or we have either a deflection head track or a slotted deflection head track, where this stud slots into the head track. The idea is it allows vertical movement. So when we look at the slotted deflection head track, or under slab movement, it's obviously going to pull and push the wall. Kind of is what it is. So head track moves, the slab moves. Then we look at the deflection head track, and there's this idea that, like, because it's just slotted in there, the studs can move with the head track. But a lot of people here have tested this, and theoretically it works, but it makes noises. But then also when you have perpendicular cross walls, it kind of locks the system together, and it all wants to move as one regardless. So essentially, these walls, while they're not structural, they're being pulled and pushed into the building. So we've had this kind of detour talking about wind, but it's like, hey, stop it. Well, we're obviously here to talk about seismic. This isn't a wind engineering conference. But kind of unsurprisingly, when you address the source of the noise, simultaneously, you're looking at the thing that's causing all the damage during earthquakes. The same mechanism that's causing the noise under wind is also what we're getting a lot of damage post-earthquake, which everyone in this room is quite familiar with. So the idea being that if we deal with this for wind, under 2-3 mils of building movement, we're also then addressing non-structural damage in earthquake under larger 30, 40, 50 mils of interstory drift. So yeah, just that point there, if we address a noise issue, we can simultaneously, look at a low damage system for both blokes. But it's just kind of, the painting the picture of how we got to where we are. So we started looking at noise, but we ended up with a pretty good system for seismic. So what are we looking at with partition damage and from interstory drift? We obviously we have our structural system, mostly reinforced concrete, structural steel. We put our partition wall in there. It's connected top to bottom like we saw. Then we get interstory drift to the building, and this head track wants to pull the wall, and we get our cracks in the wall. So the first iteration of the system that we looked at was we simply had a slot in the head track. So we moved the head track 20 mils below the slab. We put a slot in the head track, and it worked pretty well. But it worked pretty well with an asterisk in that if you only have straight rectangular walls in the building, this system here works really, really well. But the reality is, in any of these buildings that we're talking about, you always have cross walls. And whenever you have a cross wall, when those cross walls move out of plane, it then wants to pull these walls. So, you can't really just deal with in-plane, you need to deal with, in-plane and out-of-plane simultaneously. So that was our starting point, and, it worked pretty well, but it wasn't really, and then, when you start to, get this to work for out of plane, and you start putting a square peg in a round hole, and you end up with issues with implementation. So then we say, well, let's take a real step back, and is there a really low tech solution? Could we just build an isolated box within the structure? So why connect anything? So just make it completely isolated. But then what happens then if we make it completely isolated, we run into other problems. So obviously, it works when it's isolated, but then there's practicalities. Does it work in reality? Well, it doesn't really work well for firewalls, because then you need fire rate ceiling. Doesn't really work well for acoustic walls, because then you need acoustic ceiling. It also implements issues with constructability, and has a lot of cost. So people don't want to do this, but it is an option. So this is where we kind of then came in with the qubit system, where we've kind of got this bracket that sits in the head track, and the idea of the bracket is it allows out of plane and in plane movement. So just skip through to the next slide. So the idea being that if this slides in the head track in one direction, and then in the other direction, it flexes out of plane. And kind of to show you how all this works, we've done full-scale testing in Swinburne, so we build a 3x3 plasterboard wall room, and then we have this red crosshead here which is going to move, so this is simulating our interstory drift. And you'll see that this is the movement of the crosshead on the right, and then we have down the bottom left here is what the bracket does in the wall under movement. So you can see as we go, so we're doing bidirectional movement here, so you can see in one direction it's flexing, the other direction it's sliding. And the long and the short of it is it works pretty well. When we look at we push this up to about 1% drift, and under all the damage state assessments we're looking at, there's no damage to the plasterboard, no damage, no cracking. It's pretty much like they're perfectly good to go. In summary, we were looking at this qubit 360 system is what we call it, and the idea being that it addresses creaking walls under serviceability but then also eliminates damage under the kind of moderate earthquake actions. We tested this where we were able to eliminate all those creaking noises up to 0.3% interstory drift. We were able to eliminate all damage up to 1% drift. But then also the important point is the system can be tuned for better performance. So the iteration we were looking at was a 92 stud wall, and we got those results, but you can play with the system to tune it to whatever you want. Thank you. If anyone has any questions.
Thanks, Dr. Menegon.